So what we have here is a redox reaction. Things are getting oxidized and reduced, thus the name redox, but we want to balance this redox reaction. And when we talk about balancing a redox reaction, we want to make sure we conserve mass and charge on both sides of this reaction. So how do we do that? Well, the first step is to assign oxidation numbers or oxidation states to each of the constituent elements on either side of the reaction. Then we'll know who's getting oxidized and who's getting reduced. And then we can set up the half reactions, which we can then balance. All right, so let's first look at this aluminum right over here. It has an oxidation state or an oxidation number of 0. It's just aluminum by itself. And then we can go to this hydrogen. This is really just a proton right over here. It has a +1 charge, and so its hypothetical charge, you could say, well, that would be +1 as well, which would be its oxidation number or its oxidation state. And then when we get onto the right side of this reaction, we see that the aluminum now has a +3 charge. So its oxidation number would also be +3. And we can see here that the hydrogen, and actually now we have 2, so we're going to have to deal with that later on. We only have 1 here. But now each of these hydrogens have an oxidation number of 0. They're not taking up electrons or giving away electrons. You just have 2 hydrogens bonded to each other. All right, so now that we've assigned oxidation numbers, we can figure out who's getting oxidized and who is getting reduced. So if you look at the aluminum goes from an oxidation number of 0 to +3. So if your oxidation number is increasing, that means you're getting oxidized. Oxidized. You might also remember oil rig. Oxidation is losing electrons. Because you're losing electrons, you're having a more positive charge. But your oxidation number is going up, so you're getting oxidized. And if you look at the hydrogen, we're going from a +1 to a 0. If your oxidation number is reducing, you are being reduced. So reduced. So now let's set up both of the half reactions, the oxidized half reaction for aluminum and then the reduction for hydrogen. So first for the aluminum, we have an aluminum solid, and its half reaction, it is going to now a form of aluminum with a +3 charge in an aqueous state. So let's first balance this for just the number of aluminums we have. We have 1 aluminum on the left, 1 aluminum on the right. So that seems balanced. Now let's try to balance it for charge. So we have no charge here. So we should have a total of no charge on the right, but we have +3 here. And so what we need to do is add some electrons. So let me add 3 electrons right over here. And there we have it. We have balanced it for charge. And now let's think about the hydrogen. So if we have a proton on the left. Let me just do it like this. And it's in an aqueous solution. And then on the right, we just have hydrogen molecules, neutral hydrogen molecules. And so first, let us balance it for the number of hydrogens. We have 2 on the right, 1 on the left. So we're going to have to put a 2 right over here. So we've balanced for the number of hydrogens. And now let's balance for charge. So let's see, on the right-hand side, we have no net charge. While on the left-hand side, right over here, we have a +2 net charge. So in order to balance this, I have to put 2 electrons on the left-hand side. So let me do that here. So 2 electrons I'm going to add over here. And now it looks like it is balanced for charge. Now the next thing we want to do is we want to balance the number of electrons that we have on the right-hand side and on the left-hand side in these half reactions. And so how can you do that? Well, you have 3 here and you have 2 here. The least common multiple, involving a little bit of your elementary school mathematics here, of 3 and 2 is 6. So if we can get these both to 6, and how could we do that? Well, we could multiply this top half reaction by 2. So let me do that. So if I multiply this top half reaction by 2, and if I multiply this bottom half reaction by 3. Why does that work? Well, 2 times 3 electrons is going to give us 6 electrons. 3 times 2 electrons is going to get us 6 electrons. And so let me now rewrite this. So if I multiply by 2, we're going to have 2 aluminums. So we're going to have 2 aluminums in a solid state. And then on the right-hand side of this half reaction, I'm multiplying everything by 2. So now I have 2 aluminums plus 3 in an aqueous solution. And then I'm multiplying these electrons by 2 as well, so plus 6 electrons. And now let me do this down here. 3 times 2 electrons, that is going to give us 6 electrons. And then I'm going to multiply this 3 times this 2, so that's going to give us 6 hydrogen protons, I guess I could say. So plus 6 hydrogen protons that are in an aqueous solution. And then on the right-hand side, if I multiply by 3, I have 3 hydrogen molecules, each of them with 2 hydrogen atoms. And so now I have balanced the number of electrons on both sides. And now I'm going to add these 2 half reactions. And if I add the 2 half reactions, what do I get? And let me do it down here. So on the left-hand side, I'm just going to add up all of this stuff right over here. So I'm going to get 6 electrons plus 2 aluminums plus 6 hydrogen protons, And then on the right-hand side, I am going to add up all of this stuff. So I have those 2 aluminums, now with a plus 3 charge in an aqueous solution. I'm going to have the 3 hydrogens, 3 hydrogen molecules, I should say. There's actually 6 hydrogens here. And then I have the 6 electrons, plus 6 electrons. And I have 6 electrons on the left, 6 electrons on the right. I could cancel those out. And then what I have here is our balanced redox reaction, balanced for both mass and charge. And we are done.